Hey there, in our next video here, we are still working out of the yellow booklet on bonding and formula writing, but we are also leading into our next or some of the next topics with, for example, math and chemistry, and also with organic chemistry later in the year. So want to go a little bit over balancing equations because as we learned earlier in the year with the law of conservation, anything you start with you must finish with. And so if I'm starting with a certain amount of materials, I must end with that same amount of materials. Just based on that law. Okay, we cannot create, we cannot destroy, but we can change form and we can rearrange. So by this point, you should have a long time ago actually filled in all the notes for this, but I want to just show you how to actually work this. And so balancing equations is kind of like a guessing game at times. You are going to be plugging numbers around and just playing around and guessing around, but every time you put a new number in, you need to revalue and recalculate what you have. So what we have to remember is that symbols by themselves for an individual element usually do not have a number with them. So for example, Na is for sodium, Al is for aluminum, Fe is for iron, Ca for calcium. There's no numbers associated with them, but if you look at the chlorine, the oxygen, because those are the special group known as the Hofbrinkels, they're diatomic elements. And so we want to remember the Hofbrinkels. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, those also and always are listed as a diatomic, or they'll have a 2 in their formula when you're writing them by themselves. So O2, Cl2, H2, F2, Br2, I2, N2, so on and so forth. So that's only when they're an individual material, okay, or by themselves as the formula. Notice with NaCl, that's not the case. Okay, we don't see that. Notice Ca and O down here, calcium oxide, we don't see that there either. So what we have to look at, and the only place we can ever add a number when we do balancing equations is in the front in a position of a coefficient. So just like in math class, you know, you learn like 1x, 2x, 3x, 4x. That number in front, of course, is called the coefficient. That's the only place I can put a number. So when you see balance equations type of questions, there's usually a blank line or a space before. And so the way the coefficient works is kind of like in math class where you have a number in front of like a parentheses and you expand everything in there and you multiply everything afterwards. So you're going to do the same thing with chemistry. A number that's written as a coefficient will multiply everything after it. If there is an existing number, that existing number only goes with the element that's right before it. So this 2 only goes with the chlorine. This 2 only goes with the O. If we look over here, we have Al2O3. The 2 belongs to the aluminum and the 3 belongs to the oxygen. If we go down to the Fe3O4, the 3 belongs to the iron and the 4 belongs to the oxygen. If we look at this case, okay, this one's a little different. We have Pb and then we have NO3 twice. The NO3, which is nitrate, again, it's a polyatomic because it has more than one element present. The NO3, the 3 belongs to the oxygen, but the N only has 1 because there's no number after it. We don't have to write the 1, we just assume it. Again, just like in math class, you don't write 1x, you just write x. So there's 3 oxygens and there's 1 nitrogen. Again, if there's no number, that means 1. Now notice this is in a parentheses. So that means really I have 2 sets of them. I have 2 NO3 groups. So we could actually multiply inside. 2 times 3 is 6. Okay, that would be 6 oxygens. And 2 times 1 is 2 nitrogens. So we have to consider that when we're actually doing that, when we're actually bonding, when we're actually balancing our equations. So when we take a look at it, we want to see what we have first. So if we look at this, first I know I have 1 sodium there and I have 1 sodium there. That's balanced. That's okay. But I have 2 here and only 1 there. So the way we do this is by multiples. And again, once you put an answer in, you may need to change your answer and erase it and then start over. So the easiest way to try to do it is first of all, see what I have balanced. Then I know I don't need to touch those yet. Find things that aren't balanced and start to balance them. So chlorine has 2 there. The way I would balance that out is by putting a 2 in front. Again, the only place we can put an answer or change is in the coefficient. I cannot change the formula itself. Again, it's kind of like the MC Hammer rule we talked about before in previous lessons. Can't touch this, right? So I have to keep it as NaCl. The only place I can put a number in is front. So now, just like math again, I'm going to expand to this and expand to this. 2 times the chlorine, there's only 1 chlorine in this, but now it makes 2 because I'm multiplying it by 2. But that also changes my sodium. So now I have 2 sodiums. I got to come back over here, and I got to balance that out to make sure there's 2 sodiums. So when we look at our math at the end, I have 2 sodiums, I have 2 sodiums. I have 2 chlorines, and then this times this would be 2 chlorines. Now it's balanced. I don't necessarily have to write the number 1 right here. If you want to write it, it's okay. I'm not going to take off either way, but we don't have to write it. Again, you wouldn't write 1x typically in a math question. So just like this, you could leave that blank, or if you want to put the 1 in, you can. Our next one, we have aluminum and oxygen. Aluminum, again, is a single element. Oxygen is a diatomic. So there's already 2 of these, and there's only 1 of these. If we look at our numbers over here, I have 2 aluminums compared to my 1, and I have 3 oxygens compared to my 2. Now, when you have odd and even numbers, it helps to find some least common multiple that they both go into. If this is by itself, I can put any number I want here to balance out the other side, but these 2 numbers, it's going to be a little bit more difficult because they each have different numbers. They're not the same number. So what we want to find is a common value that they both go into. So we have 2 over here and 3 over here. If we just multiply them, we know what they both go into, which would be 6. So I want to make 6 over here by putting a 3 in front. So 3 times 2 is 6. And to do the same thing over here, we want to figure out, okay, well, what times 3 equals 6, which of course we know is 2. So 2 times 3 would be 6. 3 times 2 is 6. So now my oxygens are balanced on both sides. What I also have to reconsider now is now I have 4 aluminums on the right side. 2 times 2 is 4 aluminums. So easy way to fix that, all I got to do is put a 4 in front, because 4 times 1 is 4 aluminums. We have 1 iron, we have 2 oxygens, then we have 3 and 4. So this one's very similar to this. Okay, we have a single one by itself, then we have O2, but then we have other elements with different numbers. Because this is by itself, save this one to the last ending point, because we can put any number we want because it's an individual. But the 2 and 4, we have to find a balancing value. Now, an easy way to do this, I already have a common value between 2 and 4, which is 4. Okay, 2 will go into that because 2 times 2 is 4. So I don't have to change the one on the other side. Okay, so now I have 4 oxygens and I have 4 oxygens. This says I have 3 irons. I don't have to change anything here. I can just change it here. 3 irons. So balancing equations, again, is like a guessing game. You kind of play back and forth with those numbers. You may guess, and then you might have to change back again. So 1 calcium, 2 oxygens, but then 1 and 1 of each. So my calciums are balanced, but my oxygens are not. So I need to come up to 2. I can multiply that by 2, which also now means I have 2 calciums. So I have 2 calciums and I have 2 oxygens. Right now I already have 2 oxygens, so I got to make 2 calciums by putting a 2 in front. And our last one, we have sodium chloride plus lead nitrate goes to lead chloride and sodium nitrate. So this would be an example of a double replacement reaction that we learned earlier in the year where the ions are changing positions. I have 1 sodium here and I have 1 sodium way over there. I have 1 lead and 1 lead if we look at the positive ions. But if we look at the negative ions, I have 1 chlorine but 2 chlorines, and I have 2 nitrates but 1 nitrate. So we need to fix some things. If we just start here, my sodiums are balanced, but I can change my chlorines. I have 1 chlorine and 2 chlorines. I can balance that out by putting a 2 in front. But if I change that, I also have to change my sodium, because now I have 2 sodiums, where before I only had 1 sodium. So now if I put a 2 over here, I have 2 sodiums, but that also changes my whole nitrate group. It makes that I have 2 nitrates. But the good thing is I already had 2 nitrates. I had to fix that anyway. So now when we look at it again, I have 2 sodiums, I have 2 sodiums, I have 2 chlorines, I have my 2 chlorines originally, I have 1 lead and 1 lead. Originally I had 2 nitrates. Now if we multiply it, I got 2 more nitrates at the end. So again, this is balanced. So again, it's kind of a guessing game. This is just the ones from workbook, again, that was page 22. I want to do a couple more examples, and then you'll have an activity that goes along with this. So just read the description, read the details below for that activity. Okay, so here's an additional one. We have hydrogen plus nitrogen goes to ammonia. H2 plus N2 goes to NH3. So again, we have the same concept with the Hofbrinkels. There's hydrogen and there's nitrogen. They're going to be listed as a diatomic element. So I have 2 hydrogens, but I have 3 hydrogens over there. So that doesn't match up. I have 2 and 1. So in both cases, I have an odd number and an even number. We need to find some common values to do that. In both of these cases, we have evens, so it doesn't matter what number I multiply by over here, I'm always going to have an even number. So we have to consider that when we're trying to do something. I need to make these odd numbers, I need to make them even. And the easiest way to make an odd number even is by doubling it. Okay, so that would be the easiest way to start in the beginning. Sometimes that works and makes the equation balanced right away, or at least a lot easier. So if I try to double this, okay, if I try to double this, remember, we're going to expand. So now I have 2 nitrogens, which is what I started with, so that's good. But I also have to expand to this. 2 times 3 is 6 hydrogens. How do I make 6 hydrogens here? Hopefully in your head, if I have a 2, what times 2 equals 6? Hopefully you're in your head, pretty simple math, you're thinking a 3. Okay. Now, as we go through these, and as we go through other things later in the year, we'll start to talk about proportions and ratios. So what this has, because this would be a 1 here, we don't need to add it in there. Again, 3 times 2 is 6. 2 times 3 is 6. 1 times 2, of course, is 2. 2 times 1 is 2. So we're balanced. But this would be a 3 to 1 to 2 ratio. Okay, if I take the ratios of the values of my coefficients, this is in a 3 to 1 to 2 ratio. So every 3 hydrogens and 1 nitrogen, I get 2 ammonia. Okay, so it takes 3 hydrogens and 1 nitrogen to make 2 ammonia groups. So that's something we will be getting into and talking about later when we talk about mole to mole ratios or proportions, when we're talking about equations that we know are balanced, that we can then bring in other things that will help us figure out and calculate or estimate. If I know I have a starting amount, how much should I get, assuming I know my balanced equation? So here's a basic one that you guys all learned back in biology class, and we've talked about probably during the year. Basically, when you're sitting at home, you had a snack, you're going through, you're going to take in some sugars, C6H12O6. You're going to breathe oxygen, O2, and you're going to breathe out water, H2O, and carbon dioxide, CO2. Now, this one's a little more advanced because it's a lot bigger to look at, but it's not as difficult as you might think. Because if we look at all these, for the most part, we have a lot of even numbers. We have an odd oxygen there and an odd carbon there, but everything else is pretty much even. We have evens here, 6s and 12s, and then we have 2. So everything on this side is going to be even, regardless of what I put in there. Over here, it might fluctuate based on if I have an even number or an odd number. So because we're in evens, we need to eventually make those even as well. So in the case like this, we can just start at the left side because nothing is really balanced. I have 6 carbons here, but I only have 1 carbon there. I have 12 hydrogens here, but I have 2 there. What you need to consider is oxygen and elements can be in multiple places. So there's 6 plus 2, there's a total of 8 oxygens to start, and there's 1 plus 2, which is a total of 3 oxygens to finish. You have to consider the oxygens in both places. So if we just guess around, I have 6 carbons here, so let's just play around. If I put a 6 there, now I have 6 carbons, that's good. But what that does is now that changes my oxygen. So now I have 1 oxygen plus 6 times 2 is 12 oxygens now. That makes 13, but over here I had 8. So again, as you go back and forth, I mentioned in the beginning of this video that what happens when you balance equations, it's often a guessing game. Once I do one number, I got to come back and I got to guess something else. So hydrogen, I have 12. How do I make hydrogen over there? Very simple, okay? I already have 2. What's the common value with 12 and 2? Of course, if we divide them, we get 6. So now I have 6 carbons. I have 6 carbons. I have 12 hydrogen. 6 times 2 is 12 hydrogen. But now what this also does, if we look at this, if we look at these 2, that's 6 oxygens plus another 12 oxygens. That's a total of 18 oxygens. Now, notice I said we can try to play with this later because it's an even number. How do I make this 18? Well, we have to consider there's already 6 here. Okay, there's already 6 there. That means I need 12 more to make 18, because anything I start with, I must finish with. So I need 12 more oxygens. 6 of them are already there. I need 12 more. So again, this is also going to be multiplied by 6. 6 times 2 is 12. So now we have 6 oxygens plus 12 oxygens, or 18 oxygens together. Okay, that's an O, not 180. Now, as far as the ratio for this, because I didn't put a number here, this would be a 1 to 6 to 6 to 6 ratio. 1 sugar molecule, I need 6 oxygen molecules, and I'm going to get out and breathe out 6 carbon dioxides and 6 waters. Okay, that's our photosynthesis and respiration review from a few years back. Of course, this would be the respiration end of it. Photosynthesis is the exact opposite equation. 6 waters and 6 carbon dioxides would be my starting point, and I'd have 1 glucose and 6 oxygens would be my end point. Okay, so last thing I want to do and also point out when you're getting into balanced equations is the idea of polyatomics. Let me see, we're going to change this around a little bit. Let me just grab this one thing here. Just pulling this one off the top of my head as an extra one for you. Using table E, which I believe was page 23. Okay, so again, using some of the table E ones. I just want to remind you of how to pull some things out, okay? Now, I pulled a couple things out. More so, this was the polyatomic OH, or hydroxide. And the hydroxide ion, in reality, this is a base and this is an acid. Potassium hydroxide, hydrochloric acid, makes a water and some type of salt. Potassium chloride is a salt. HOH, we learned earlier in the year, we learned about, for example, dihydrogen monoxide, right? It's just another way to write H2O, okay? If you see H2O, H2O is the same as HOH, because in reality, the molecular structure looks like this. It's one hydrogen attached to an oxygen. On the other side of it is another oxygen. So really it's HOH. So when you're seeing something like this, what I want you to look at and focus on, if you have polyatomics, if you're balancing polyatomic equations, focus on keeping groups together. Again, like the MC Hammer rule, can't touch this. So keep the group together. You don't have to go through every single element and figure that out, but in some cases it helps. So I have 1K there, I have 1K there. I have 1 Cl here, I have 1 Cl here. I have an H here and an H by itself, and then I have an OH group and an OH group. Okay, so if you can try to keep them together, try to keep them together. On the previous page, or the first part of this video when we were looking at page 22, 22 I believe it was, One of the last questions at the bottom had a polyatomic, and I was looking at the NO3s on one side and the NO3s on the other. I wasn't looking at every single N and every single O. I was keeping those groups together. So that's just a little strategy to follow along when you're going through this. So I know this is maybe a little bit longer than our other videos. Hopefully you found some benefit. If you have any questions, just leave them below, or comments, leave them below. But like I said, you do have to guess and you do have to play around with your numbers. But at the end, what you need to do, every time you add a number, the key thing is always to recheck your values to see how many elements you have of each atom, or each type, or excuse me, how many atoms you have of each type of element on both sides. Because remember, everything on the left of the arrow has to equal the same thing on the right of the arrow. Again, that's law of conservation of mass and matter. Anything we start with on one side, we have to finish with on the other side. So make sure you read below and or check the assignment to know what questions and or what worksheets you can do to work with this. All right, we'll talk to you later.